what we've just done, therefore, is look up now a way of measuring the masses of many astrophysical systems. Because from this virial theorem mass that we've just derived, it's straightforward. You take a picture, an image, to get R. You take some spectra to get V, and that gives you the mass. So now we can measure masses and we can measure light. And what that gives us is something called the mass to light ratio. And it's a way of determining the dark matter content. And a very common thing is we say m over L equals 1 for one solar mass. So this little circle dot, that's solar mass, divided by one solar luminosity, i.e. the sun has an m over L equals 1. And then we can look at lots of other things. So I'll just insert this here, trying my best to make it a bit larger. I'll have to go on to the next page to do that. So here's a load of things which you can look at. So the sun, by definition, has a mass to light ratio of 1. Open clusters, so these are small star clusters in, around the galaxy, youngish stars. And they also have a mass to light ratio of about 1. It varies a little bit, but about 1. If you go to here, this is the globular cluster. So globular clusters have ancient stars. So basically all the stars like the sun have already evolved and become white dwarfs. All the more massive ones have already exploded as supernovae. Ancient stars. So all of the mass is actually less than about 0.6 times the mass of the sun. And since you've got this relationship between mass and luminosity, you actually have quite a high mass to light ratio in a globular cluster, about 3. That doesn't mean there's 3 times more dark matter in a globular cluster than there is locally. What you're actually seeing here is that this is just because of old stars. So there's not a lot of evidence for dark matter sitting in globular clusters. On the other hand, you've got spiral galaxies here. The mass to light ratio of spiral galaxies is something like 5. Spiral galaxies also have quite a lot of young stars. So there is dark matter here. Elliptical galaxies, this is where you have to use the virial theorem to measure the mass. They have lots of dark matter. And galaxy clusters have even more dark matter. I.e. mass to light ratios can be 50, 100, or even more. So there really is an awful lot of dark matter which exists in larger and larger structures. In general, bigger structures are progressively more dark matter dominated. And that tells you something, about how dark matter might behave. In particular, there are also a small population of things called dwarf. Oops, not dwarf. Called dwarf galaxies. In particular, dwarf spheroidal galaxies. And these are low luminosity, they're low mass, but very strongly dark matter dominated. So i.e., take a globular cluster, so here the mass is about 10 to the 6 solar masses. The radius is, it's a few parsecs. And if you take a dwarf spheroidal galaxy, the mass is perhaps 10 to the 7 solar masses, and the R is perhaps 100 parsecs, so they're much lower density. But in this case, you've got no dark matter, and in this place you have lots of dark matter. And in fact, these dwarf spheroidals are weird because they're some of the most dark matter dominated places in the universe. So there's a bit of a puzzle there. But what this leads to is the concept, it's very important, bigger structures end up with more dark matter. And that must tell you something about how dark matter behaves. And in turn, that leads to an idea of something called the dark matter temperature. And we talk about temperature, what we really mean is a velocity. And so dark matter consists of something, we don't know what it is, whether it might be an elementary particle, it might be an astronomical object, but it has some characteristic velocity at which it moves. And so dark matter, it might be hot, and that means that it's relativistic. It might be cold, i.e., hundreds of kilometers per second or less, or anything in between. So if you look at literature, you'll see things like, warm dark matter or tepid dark matter, or all sorts of different temperatures of dark matter. And the point is that the behaviour of dark matter is different according to the temperature. And so if I look, for example, now at simulations of what dark matter will do, what we have on the left here, this is actual data. So this is the distribution of galaxies in space. And this is simulations of cold, warm, and hot dark matter. And you can kind of see what happens. So if hot dark matter is hot, the particles move very quickly. If you think about structures having potential wells, they have some escape velocity. So if particles move quickly, they can go past that escape velocity. If they move slowly, they're captured. And so if dark matter moves quickly, it doesn't fall into the potential wells. It doesn't make them more massive. Therefore, they don't collapse and become these dark matter dominated structures which create the large scale structure we see. On the other hand, if dark matter is cold, up here, you have low velocity and you fall into the potential wells. And when you do that, you make small scale structure. Whereas with the hot dark matter, you wash out small scale structure. And so you can sort of roughly look at this and ask yourself, well, what is the dark matter temperature that we prefer? And the answer is, observations and in various lines generally prefer cold dark matter. It's why our benchmark universe is called lambda CDM. It stands for cosmological constant cold dark matter. And so, that is roughly what we're looking at. It's not completely simple. There is one problem with cold dark matter that's worth being aware of. And that's something called the substructure crisis. And what the substructure crisis tells me is that I make too many small structures. So if I think I have another photo here, so if I insert that, just look at this here. This is showing me the velocity dispersion. So V, which is roughly equivalent to the mass, against the number. And so these are local dwarf galaxies, basically, that sit in here. So these are all the observations along this line here. On the other hand, the actual simulations of cold dark matter are up here. And so for a little while, people have been quite worried about the idea of what's called this substructure crisis. It's not really easy. You can make things warm, you can make things self-interact, you can do all sorts of things. In practice, there are multiple potential biases. There are solutions. So when I was a PhD student, this was a real crisis. I think most of them have now gone away. So you can, for example, have interacting dark matter, in particular self-interacting dark matter. You can have a very simple thing, which is, of course, this is telling me where the dark matter is. What if not all the dark matter has baryonic matter with it? In other words, what if some of the halos sit here actually don't have any stars? So some dark matter may not have stars. That's another possibility. And there's also just the possibility of some observational bias. These are faint little galaxies, they're hard to find. So in general, people are pretty happy with the idea that this here can be explained away, this gap. And it's a big gap, remember, this is a logarithmic plot, so it's a factor of 10 at least. That gap can be explained away, and therefore that indeed our benchmark universe should be this one here, lambda CDM. And then the next thing we need to ask ourselves is, what are the properties of dark matter and what actually are the candidates for it?